Welcome back. In this chapter, we're going to start time series analysis, and we'll continue that for the next chapter through 15. And one of the main uses of time series is to do forecasting. So we'll spend a lot of time looking at how to do forecasting and how to evaluate how good your forecasts are. And before we even get to that point, we'll spend some time talking about how to build a good model. How many lags. When you use time series, you often end up using lags of the endogenous variable. How many lags should you use? We'll look at a concept called stationarity. We'll deal with serial correlation and some other issues in the next two chapters. And so this brings up something that I guess I should point out. When you think about econometric models, there are two uses of those models. One is to learn about the world, and another is to do forecasting. And the models you use for that aren't necessarily the same thing. So you might imagine some model where you had consumption at time t is beta 0 plus beta 1 times disposable income, let's just call it disposable y at t plus some error. Now we'll build some time series models that are a little different than this. Normally we would want some lags of c on this side for reasons we'll explain. And this is often yt minus 1 rather than yt. But let's just imagine this is our model. And in this case, and we'd also want to include a bunch of other things that might explain consumption. The reason we have lag consumption is recent past consumption might matter, right, for your consumption today. If you're used to spending a lot of money, even if your income falls this year, you've got a lot of bills, house payments and things that will keep you on that other trajectory. And so your income may not change as much as your consumption may not change as much as your income fell. And it's because of that habit persistence. And so in that case, you'd want to include lag Cs. It may be that your income yesterday and the day before has something to do with your consumption today. You might want to include wealth in this because consumption doesn't just depend upon income, it depends upon wealth. And then you can imagine two people with zero income, or let's say $1,000 worth of income per month. Not very good. The one person has 500 million in assets and wealth, and the other has zero. Well, the consumption would be higher for the person that has a lot of wealth. So we'd want to add controls and other sorts of things. But just as an example, let me just talk about this. This beta 1 would be the marginal propensity to consume. And we might want to know what's the true value of the MPC. And is it constant over time? We might want to check to see if this beta 1 changes at certain points in time. Like, is it different in recessions as compared to when we're near full employment and those kinds of questions. So we'd want to know what's the true value of the MPC. So if we're trying to learn about the world, we're going to want an unbiased estimator of the MPC. We wouldn't want if we're trying to find out the true value of beta 1, we wouldn't want to employ a biased estimator. When it comes to forecasting, we worry less about the accuracy of the coefficients. Sometimes they might be biased. What we worry about is how accurate the forecasts are. So you might have two different potential models. So this is the distribution of your estimator of beta hat 1. And here's the true value of beta 1. And so we have these estimators. Now, an unbiased estimator means the average value is going to be beta 1. And so suppose we have one estimator that has a normal distribution that looks something like this. It has very long tails. And so although on average we'll get this true value, a lot of times we're going to be pretty far off because of this huge variance in the distribution. You might have another estimator that's biased, not a very good normal distribution there, but that's supposed to be a normal distribution with really short tails. In this case, you're going to your average value is biased, and so you're not going to get the right value of beta 1 on average, but you're going to get much closer to the true value on average because of this really small variance. And what that means is you're probably going to forecast consumption much better with this model, even though it's biased, than you would with this model, which has an unbiased estimator. And so what we worry about is this average distance between the estimator and the outcome. In this case, that average distance, the 95% confidence interval might be something like that. And so the average distance between the truth and what you're trying to find out is going to be pretty large. But if you did this over and over and over and over and over, the law of large numbers would give you the true value. This one, you'd never get to the true value, but you're going to be much closer on average. I mean, the 95% confidence interval might look something like that. And so you're going to be in that tiny range. You're going to have a little bit of bias, but you're going to have better forecasts on average with that kind of a model. And so with forecasting, as opposed to the search for truth about the world, we worry less about the bias in the coefficients, and we use something called the root mean forecasting error to evaluate the accuracy of the forecast. So that's where we're headed. Now, a typical time series in economics, we plot them by putting time on this axis, and something like, let's just look at GDP at t. This is really, well, it doesn't matter. You probably want to plot the log of GDP rather than GDP, but we'll come to that later. But anyway, what this would look like is something like a noisy series. You hit the Great Recession and it drops, and I haven't probably exaggerated the noise in the series enough. But you'll see the point is that you'll have this upward trend. It's good times, recessions, there's some average. We hit the Great Recession, there seemed to be a drop, and then we went back on the old growth path. I'm exaggerating what happened in 2007. So this might be data from 1960 to say today. Well, not quite today. We don't have GDP data for this quarter yet, but through the latest data we have, and it looks like this. Now, there's some features of this that are going to make the econometrics trickier than what we've encountered so far. The first is the fact that this thing grows over time, it moves upward over time. This is really the log of GDP. Actual GDP would have more of a curve to it. It would grow more exponentially. But anyway, this upward trend in GDP is going to mean that the average value here is different from the average value here. And the fact that the mean of this series is changing over time, if we were to, if we could somehow run the economy over and over and over, we can't do this, but suppose that we could take the US economy just into a laboratory and run GDP from 60 to today over and over and over again. So we get a bunch of these pictures. The recessions and things may be a little different because the randomness would be different in the economy. But you can imagine then that you could think about what's the average value here of all those different runs of the economy. It's certainly going to be higher than the average value here of all those different runs in the economy. So the mean value of GDP changes over time, and that creates some special problems. That's called non-stationarity. The other thing that happens in time series is you have to worry about these breaks. So it looks like there's a break in the series at this point. There may be another one in 1982 if you were looking at monetary policy, because the monetary policy rule changed then. In the 70s, we went off Bretton Woods. That probably changed coefficients and put jumps in series like this. And so those breaks, if we use this model to forecast, we're going to get it wrong, because it's going to put us on a trajectory that's above this one. So we have to have a method for testing for these breaks, and we will. The third thing, suppose this is the trend up to this point, and then somehow there's a break in the trend. We still don't know, though it's been pretty long yet, if this is going to ever come back to trend fully, but it looks like it's not going to. It looks like this drop was probably a permanent change in the structure of the economy. The third feature that we're going to need to deal with is these boom times and these recessions. They last more than one period. So when we're above the mean in one period, we're likely to be above the mean in the next period. And that's called serial correlation or autocorrelation. And we have to deal with that. It's just like the temperature. If it's in the summer and the average temperature is 85 and it's 100 today, it's likely tomorrow it's going to be above the mean as well. It may not be, but it's very likely that those high temperatures will persist. In the economy, GDP above trend will persist for a while, then you'll go below trend for a while and above trend. I mean, if those things were truly random, they'd just jump around. You wouldn't see these waves. You'd see this up and down movement with no real pattern to it. And so this serial correlation is the third thing that we're going to need to deal with as we begin to look at time series. Okay, let's do some definitions. There's some terminology we're going to need for talking about time series. It's obvious, but let's do it anyway. So some terminology. The first thing is the first lag of a series yt is yt minus 1, obvious. The jth lag is yt minus j. So when we say the jth lag of yt, we just mean yt minus j. Now, one thing I want to point out is that when you lag variables, you lose observation. So suppose you had an Excel spreadsheet. I don't know, here's column A, here's column B, 1, 2, 3, 4, 5, 6, 7. And you've got numbers here, 3, 5, 8, 9, 11, 16, 20. I'm making it grow at an uneven rate like a time series generally does. So this is what we call the level. This would be yt, and this would be the lag. This would be yt minus 1. Well, what I would do in the spreadsheet is I would just tell it to take this cell minus this cell. I'll explain on the video for the lab how to do it in the package. It's pretty easy. You just put d dot in front of it. If you want the second lag, you do d2 dot, name a variable. But we'll get to that in the other video. So I can't difference this series because there's no observation that comes before it. So my first difference here would be 2, 5 minus 3, then 1, then 2, then 5, and then 4. So this would be y. Oh, I'm sorry, I'm differencing. That's not what we're doing yet. When we get to differencing, we'll do that. If I want to lag this series, the first observation here, this is yt. This needs to be yt minus 1. So this will be 3, 5, 8, 9, 16, 11, sorry, and 16. So this is yt, this is yt minus 1. So you just put those observations there. But notice that we've missed an observation here. So instead of having 7 observations, we lose 1 to 6. If I do the second lag, yt minus 2, I'm going to lose 2 observations because what's the second lag of 8? There's the first lag. This is y3, first lag, second lag. So this is going to be 3, 5, oops, the column's off a little bit, 3, 5, 8, 9, 11. And now we've lost 2 observations. So you lose as many observations as you have lags. So just be aware of that as you go through this. Okay, the first difference of a series, let me take off the, so this was yt. This was yt minus 1. The first lag of a series, delta yt, the first difference, geez, the first difference of a series, we denote as delta yt, and it's defined as yt minus yt minus 1. Now, it's possible to have a second difference, a third difference. You could difference this again, but in economics, we generally just use first differences, so I'm not going to go through that. Again, because it involves a lag of a series, you're going to lose an observation. So if I put column C here as delta yt, this is what I did mistakenly before, I can't take the difference here. I can't take the lag because there is no lag at this one, but I can difference this one. So I lose the first observation, and then I'll get 2, 3, 1, 2, 5, and 4. That minus that, that minus that, and so on. So that would be the first difference of a series. And again, you can do that in the software package pretty easy. I said a moment ago that the lags were d dot. I was thinking of differences. The lags, as I'll explain in the video for the lab, are L dot. If you want the second lag, you do L2 dot, name of variable. If you want the third lag, L3 dot, name of variable. For differences, you use d dot, and it'll work for you. All right, so that's the first difference. So lags and differencing. Whenever we have this problem called non-stationarity, differencing will normally be the solution, as we'll talk about. The other thing that's really common in economics is to take logs. So why take logs? Why is it that logs are so popular in economics? One reason we talked about in 320 is it helps you capture nonlinearities in the data. With time series, though, it's really because, first, that many series, such as GDP or prices or consumption and all sorts of things, grow exponentially. If you have a constant growth rate for a series, say you're looking at a series over time, I was going to say YT and I ended up putting the Y there. Some series YT that grows exponentially, it'll look like this. It'll just keep getting higher, growing and growing and growing. And so it'll shoot off to infinity. Well, that's not linear. This is a nonlinear. This is what we talked about in 320 a little bit. We need a linear representation. And so you could model this as YT equals E to the, what do I want to use here, beta or alpha? Alpha t. This alpha is the growth rate. If it was 3%, you'd have a 3% here. And this would give you could model this and it would look something like this. You could generate this on the computer. If you take the log of YT, what will you get? Well, you'll just get alpha t. And what that looks like over time is a linear series. So it just grows at the rate alpha. And so this will linearize these series that grow at an exponential rate. You could even, if you want to, write the model as y equals alpha naught e to the alpha 1 t e to the ut. So this still grows exponentially. You just have a coefficient out in front to normalize it. This is yt. If you took the log of yt, what would you get? You'd get the log of alpha naught plus alpha 1t plus ut. And we could just give this some other name like alpha tilde naught. That's just a constant. And so you'd get a standard old looking regression model that's linear with some errors. And so in this case, you'd start here at alpha 0. I think I might have not started at the origin when I didn't have a constant, but I should have. There's the alpha t part. There's the alpha tilde naught part. Then the actual series will randomly vary around this because of the ut. And if this is serially correlated, we'll get the kinds of patterns that we see in time series. And so it takes these series that grow exponentially and it turns it into a linear series that we can work with using the tools of econometrics, which are generally linear. The other reason, so the second reason why we take logs is that the standard error of many time series grows over time. So imagine an economy that over the course of, 100 years maybe, who knows, starts with consumption equal to 1,000 way back when for some time period. And over time, consumption grows to 50,000. Become a much richer country over time. The variance in consumption over time here, it really can't go below 0, and it can't go much higher. It could go a little. The variation in consumption here around this 1,000 would be much smaller than the variation here. And so if you were to look at how much consumption's varying over time way out towards the end, it'd be much larger than it is in the beginning. There's just not much consumption here. I mean, last year consumption might have been 48,000, 47, might be 53, and then 51. I mean, the standard deviation might be higher than the actual level of consumption at this time. You know, this might be plus or minus 300. This might be plus and minus 3,000 or 4,000. It's a much bigger standard error. By taking logs, taking a log of the series, makes the standard error constant, or at least approximately constant, close enough for econometric work. And so we almost always take logs of the series. You wouldn't take a log of something like the interest rate because it's already, it doesn't have this problem. But so generally you'd look at a series, and if it's growing over time, you'd want to take the log of it. An interest rate over time tends to vary around some constant value, and taking a log isn't important. It's already a percentage change too, which brings me to the next topic, which is growth rates. Once we've taken the log of a series, it's very easy to define what the growth rate is. And so the growth rate of a series is the log of yt minus the log of yt minus 1. That's generally the way we measure the growth in yt. And you can write this as delta log yt equals this, because it's the change in the log of yt. So in the software package, you'll just take the log of yt, then difference it, and you'll have the growth rate. Why does this work? I'm not going to prove it, but let me just give a very rough explanation of why that works. If I have a time series yt, the log of yt, and I differentiate it, d log yt, that'll be dyt over yt, right? And that is the percentage change in yt for an infinitesimally small change. And so, because it's just the change over the level. If yt was 100 and it changed by 10, that would give you 10%. It would be a 10% change. So this gives you the right way to calculate a percentage change. In discrete terms, we could say the change, how do I want to do this? In discrete models, in discrete time, we could say delta log yt is ln yt minus ln yt minus 1. This is just a discrete form of this. And so this is going to give us, as long as these changes in yt are small, because remember this is based upon a small change in yt, as long as the changes in yt are relatively small, and they generally are in economics, then this is the right way to measure a growth rate. If you were looking at inflation, though, in a hyperinflationary environment, where the changes are huge period to period in your data, this type of a calculation of the growth rate would not work very well. But it's a really good approximation of growth rates, a really simple way to calculate them, and it's the way it's generally done in time series econometrics. Okay, so lags, differences, logs, and growth rates are the terminology we were trying to explain here. Okay, let's move on to this notion of serial correlation. And so we want to talk about autocorrelation. Oops, that's just one word. Autocorrelation. What the heck is this? As I said, many time series are correlated over time. And we'd like to know how correlated they are. And so, because, like we were talking about the weather example, today is correlated with yesterday. If it's above mean today, yesterday, you're likely to be above the mean today. It's less correlated with the day before, less correlated with the day before that. Certainly the weather 3 months ago probably doesn't have a lot to do with predicting the weather tomorrow. And so the correlations die out over time. The weather today is much more correlated with the weather yesterday than with the weather 6 months ago. So we want to know how those correlations change as we move the days or the quarters or the years far apart. So the first autocorrelation is simply the correlation of yt and yt minus 1. The jth autocorrelation is the correlation between yt and yt minus j. Where if j was 0, this would just be, well, you basically get the variance. This would be 1, because the correlation of yt with itself is 1. Never mind. But when j is 1, you get the first. When j is 2, you get the second autocorrelation. J is 3, you get the third, and so on. So that's just the notation that we use to denote these autocorrelations. It's just like standard correlations, yt and xt or something like that, except we're just looking at a correlation with yt in the past. Now, as I was saying, we would expect this to be much larger than, say, when j equals 6, because the correlation tends to die out as we move over time. The definition of this, so rho j is equal to the covariance over yt minus j. This is the correlation of yt minus j. Oops, didn't leave myself enough room there. We write that correlation as rho j, and it's defined as this covariance, just like this is exactly the same formula we've used before for correlation. We just plug in t minus j and yt, except instead of y and x. And so this is over the square root of the variance of yt times the variance of yt minus j. If you put the xt everywhere for yt minus j, you'll get exactly the same correlation estimate or correlation definition that we've used all along. So we're just generalizing what we've done all along to time series. Now you won't actually have to do this because there's a nice, really simple function in Stata that will do this automatically for you in a single command. But if you wanted to estimate it, you would just take the estimator would be the so that the correlation of yt minus j hat, the estimated correlation, is just the estimated covariance of yt minus j hat over the estimated variance of yt hat. Now what happened before down here, this was the square root of the variance of yt over the variance of yt minus j. What happened? Well, later on when we talk about stationarity, which we haven't really covered yet, we'll argue that stationary means these have to be the same. The variance can't change over time, or we have a non-stationary distribution. So these two variances are equal. And so you just get the variance squared, square root, which gives you that. And so under the assumption of stationarity, which we'll always need to be able to do anything, this is what you get. So you would just take this. Now the covariance itself, covariance hat of yt, the estimated covariance, it would just be this formula. It would be the 1 over t times the sum from t equals j plus 1 to cap t. I didn't leave myself enough room here. Y bar j plus 1 comma t. This should be times, and I'm going to put it down here, times yt minus j minus y bar from 1 to t minus j. So again, this should be multiplied here. I just wasn't sure if you could see it. I'll go ahead and write it in case you can. I'm never sure how far the camera goes to the right here. I think you can see that, but if not, it's here for you. So this is the formula here, and this is just in case you can't see that. All right, so some things about this. First of all, notice that it starts at j plus 1 rather than 1. Why? Because remember that if we have j lags, we lose j observations. So our first observation we can use is j plus 1. When I plug j plus 1 into t minus j, I'll get 1. So this is y1 when t is j plus 1. We couldn't go back any further than that. This just means the mean calculated from j plus 1 to t. So this is the data range. And it goes from j plus 1 to t. For yt, that's all the data that's available. For yt minus j, it goes from 1 to t minus j, again, because of the available data. So this is just accounting. This notation is just accounting for the fact that we've lost j observations. So this is the formula that you would use to calculate it. It's just basically the average 1 over t of the covariances in each time period. All right, where'd my eraser go? Oh, there it is. So yeah, in the software package, you'll just press a single button and that all happens automatically. But you need to understand what it means. Okay, now let's go to autoregressions. Autoregressions, auto, self. We're going to regress something on itself. We're going to regress yt on its lags, or whatever time series we're looking at, yt, xt, whatever we're calling it. So the first order model first order autoregression we call an AR1, autoregression of the first order. And that would be written as yt equals beta naught plus beta 1 yt minus 1 plus ut. And so we're regressing yt on its first lag, and that gives us ut. We're regressing yt on its first lag, and this is a description of that model. This could be, the book has an example where they look at GDP from 62. This is the growth in GDP. I'll just write it like the book does. So GDP at T, GDP G, growth at T, is 1.991. This is just from OLS, plus 0.344 GDP growth at T minus 1. Then you have your usual standard errors, 0.349. And as always, as we'll explain later, we're going to want to use HAC errors, robust errors. So you could just take a model like this. You could regress inflation on inflation yesterday. You may need more than one lag. And so we'll extend this in a minute to a pth order model. And then once we've done that, we'll add some x's, because we may want to have those x's in the model too, as we'll explain. So let's wait to move to the pth order model and just work a little bit with this AR1 and talk about forecasting. So let's talk about forecasting and forecast error. Forecast and forecast error. So suppose we have a model. So to forecast using an AR1, first you would estimate yt equals beta naught plus beta 1 yt minus 1 plus ut. Now whether you can use OLS or you need to account for serial correlation and other things we'll talk about later. For now, just estimate this somehow. Let's suppose UT is IID, no correlation. Then you could just use OLS. Then you've got your estimates. So to forecast y t plus 1, use y hat t plus 1 given t, explain this in a second, is beta naught hat plus beta 1 hat yt. No hat here. We know this. That's in our data set. That's the last y in our data set. We can estimate this through yt and then use it, because we could just forward this one period. The second period the equation would be yt plus 1 equals beta naught plus beta 1 yt plus ut plus 1. You can just forward everything, all the t's, one period, and you get this. Then you can use this as your basis for your forecast. You don't know this. You never know the errors. You don't even have an estimate of it. But you can use the expected value of that 0. So we just set it as expected value, plug in the estimated values. We know what this is. We do it for the tth period. And this t plus 1 given t says, this is our estimator of y hat t plus 1 based upon data through time t. Then we could go, we could continue this. So we could keep going. So we could keep going. So we could say that y hat of t plus 2 given t is beta naught hat plus beta 1 hat times y hat t plus 1 given t. So we've just estimated y at time t plus 1 based upon data through t. We can use that estimate to forecast y t plus 2 based upon data through t, and we would do that. And then I could use this to get yt plus 3, use yt plus 3 to get yt plus 4, and go as far out as I want. Now, the further we go out, the worse those forecasts are going to be. By the time you go out pretty far, if you've got a stationary model, you're basically just forecasting the mean of the series. So we can use this iterative process to produce forecasts. That'll work also with an ARP. And so when we get there, you could do the same sort of thing. Then we could talk about the forecast error. And that's going to be the actual value at t plus 1 minus y hat t plus 1 given t. The difference between the true and the forecast. So that would be the forecast error. Now, we don't know this. We're at time t. If we had t plus 1 data, we wouldn't need to forecast it. So we only have data through time t. We can't actually do this until t plus 1 actually happens. So we make the forecast for next year, then we have to wait till next year rolls around before we can calculate this forecast error. There's something we'll look at later called pseudo-forecasting that will allow us to immediately evaluate our forecasting ability in the model, but we'll save that till the end. Okay, just a quick note. This is just a terminology note. When we talk about predicted values, those are in sample. When we talk about forecasts, those are out of sample. What we just talked about were out of sample forecasts. Our data went up to time t, and we forecasted t plus 1 and t plus 2, t plus 3 if we want. Those are forecasts because they're beyond our sample, they're out of sample. You can imagine estimating the model through time t, and then using that model to go back and forecast values within. So you could estimate, for this one, you could estimate yt equals beta naught hat plus beta 1 hat yt minus 1. And then you could say maybe for the 8th observation, which is in your sample goes to 100. You're going to look at the 8th. Say, well, y8 hat given t, given 100, you don't usually do that for this. This is just a predicted value. Y8 hat is beta naught hat plus beta 1 hat y7. That's a prediction because it's in sample. You've estimated the model with all the hundreds, and then you're going to forecast within the data that you use, or predict within the data that you use. These are usually way more accurate than these. Okay, back to the forecast error. Now let's talk about something called the root mean square error. So the root mean square forecasting error. So this is a measure of the size of our forecasting error. So the root mean square forecast error is defined to be the square root of the expected value of y t plus 1 minus y hat t plus 1 given t squared. So this is the expected squared deviation. We then take the square root to get this, basically the standard error. If you don't have the word root in front of this, just mean square error. It just means this without the square root. So this is going to be a measure of the size of our forecasting error. So this embodies two sources of error. The first error is due to the future value of ut is unknown. We don't know ut plus 1, so we just set it equal to the mean, 0. If we knew it, we could get a much better forecast, but we don't. This is generally the main source of the error when n is large. So there's also an error from using estimates, beta hats, instead of the true values. If we knew the true values of the coefficients, our forecast would be more accurate. We're using estimates. That's going to throw us off a little bit. Now, so this first is almost always, it's generally much larger than the second. And if n is large, I'm saying n, we say t in time series. I'm going to have to erase this to make room. I'm sorry. When t is large, sometimes it isn't. We'll cover that later. But when t is large, the first source of error is much greater than the second. So you can just sort of ignore the second one. In that case, the root mean square forecasting error is approximately equal to, nice approximate, is approximately equal to the square root of the variance of ut. And that's just another name for the standard error of the regression that we've talked about all along. It's just the standard deviation of ut that comes out of the it's just another name for the standard error. Okay, to forecast it, this is actually the forecast. So the estimate of this would just be the standard error from the regression from your printout. It would be the estimate of that. So when t is large, it's really easy. You can get this root mean square right off the printout from whatever regression that you're doing in the usual way. Now, as we'll talk about later, though, there is some, in time series, it's often the case that you can't justify a large t. I mean, if you've got 30 years of quarterly data, which is pretty long for us, in macro, because of the structural break in 82, the data often goes from 82 through today. So let's just say 30 years. and it's quarterly because you want to use GDP and you don't have monthly data available, nothing you can do about that. You have 120 observations. That's not a lot and may not be enough to justify that. When the statistical packages calculate the root mean square forecast error, we'll talk about this later, but I'll just mention it now, they will allow for both types. But just wanted to mention that when n is large, you can usually do this. The book then goes through an example. I'm not sure it's necessary. They look at an example where they estimate GDP growth at t is 1.991. I think we wrote this down earlier, plus 0.344 times GDP growth at t minus 1. Then what you could do, the last data point is 2012. In this data set, in the lab stuff, we'll use data right up to today. Actually, I'm going to cut it off at the Great Recession, so we don't have to deal with structural breaks. But we'll use data that goes a little farther than this. That was equal to 0.15%. Not very strong. So if you forecast GDP growth hat 2013 Q1 given 2012 Q4, because we've estimated the model through here, it would be 1.991 plus 0.344 times 0.15, and then you'd get 2.0. So your forecast would be a 2% growth rate. Basically, your forecast is always going to be 1.991 plus some fraction of what happened yesterday. This is the serial correlation, the persistence part. The actual Y2013Q1 was, what was it, 1.1%? 1.1%. And so your forecast error would be what? So the forecast error would be equal to 1.1 minus 2.0, actually minus 0.9%. Now the standard error of the regression that comes out of this when you estimate it is 3.16. That's like saying that one standard deviation around the mean, you have plus or minus 3% in your forecast. That's a huge band. And so on average, these forecasts are not going to be very good from this model. Now, there may be lots and lots of things. This is just a very simple model for illustration. There may be lots and lots of things we could do to improve those forecasts quite a bit. We'll talk about some of those later. All right. Now let's generalize to the Pth order. Autoregression. So the Pth order autoregression model. And we designate this as ARP. So it's what you would probably guess, yt equals beta naught plus beta 1, yt minus 1 plus beta 2, yt minus 2, all the way out to beta p, yt minus p plus ut. So because we're using p lags we're going to lose p observations, or this would be from t equals p plus 1 up to t would be our data set, because you lose those first p observations. You could forecast this from the same way. So yt would be beta naught plus beta 1 yt minus 1 out to beta p yt minus p plus ut. You could then take it one period ahead. Yt plus 1 equals beta naught plus beta 1 yt plus beta p yt minus p plus 1 plus ut plus 1. And then just take the estimated values of the betas from when you estimated this. It's just OLS of yt on p lags if the error term is uncorrelated. And you know all these y's. They're in the data set, and that would give you yt plus 1. So yt plus 1 given t would be this. And then you'd set the ut equal to its mean because you don't have any idea what it is. So that would be your forecast. Then you could do y hat t plus 2 given t. That's going to be beta naught hat plus beta 1 hat y hat t plus 1 given t plus beta 2 hat. I don't need an estimate here because I know what it is, yt plus beta p hat y cap t minus p plus 2. Or 1. 2, yeah, I've got another period ahead. And if I went to t plus 3, this will become, I'll need a hat here and so on. And you could just keep going as far as you wanted with this kind of a model. And then you would evaluate the forecast in the same way. You would just look at y hat t plus 1 given t minus the true value minus the forecast would be the forecast error. So there's nothing different here really except that we've generalized the model. Now there's an important assumption for ARP models. We'll look at more general assumptions later. This is just one, but you need, as usual, the expected value of ut given all past y's, yt minus 1, yt minus 2, and so on. That has to be 0. So the error has to be uncorrelated with all of the past y's. So this implies that the errors are serially uncorrelated. See, suppose that yt, let me just use it AR1 to illustrate this, plus beta 1 yt minus 1 plus ut. And suppose ut has a similar structure, ut minus 1 plus, say, et. So ut is also serially correlated, so is yt. Often when ut is serially correlated like this, that's an indication your model's misspecified. But let's just suppose this is the model. Well, look, that ut and yt are going to be correlated because when ut moves, yt moves. So that's clear. Those two things are. So it must be that yt minus 1 and ut minus 1 are correlated in the same way. If I wrote this for yt minus 1, this would be ut minus 1. So they're correlated. So yt minus 1 is correlated with ut because ut has ut minus 1 in it. So in this case, this assumption wouldn't be satisfied. And we'll talk about this in chapter 15 when we have this kind of thing happen. How do you solve it so you can estimate this properly? And we'll talk about how to do that later. But so the implicit assumption here is that the errors are serially uncorrelated that comes out of this. it also implies, so 1, 2, that y t plus 1 given t is the expected value of y t plus 1 given y t back to y t minus p. This one goes all the way back to y1. This only goes back p1. So if t were 100, 25 years of quarterly data, and you had 4 lags, this would only require the observations from 100 to 96, t minus 4, because we have 4 lags. We're using an AR4. So you'd only need those 5 pieces of data, yt, t minus 1, t minus 2, 3, and 4, 5 pieces of data to estimate this. Anything beyond that doesn't help you. So it says that when you use this model, you don't have to use any lags past t minus p, that using this model is correct, that the best forecast doesn't need anything past the pth lag in an ARP model. And then the book goes through an example where it estimates an AR2 for GDP. I think that's pretty obvious how you would do that. You would just regress yt on yt minus 1 and yt minus 2. And that's all there is to it. So take a look at that example. And let's begin to generalize this model. So now let's go to time series models. With additional predictors, with additional regressors. The book calls them predictors, so I'll say that too. But it just means additional right-hand side variables. So this is called the ADL model. And that stands for autoregressive distributed lag. And so the book illustrates this with an example. Maybe I'll do that first. But basically what we're going to do is just like a model, something like yt is beta naught plus beta 1 yt minus 1 plus beta 2 x t minus 1 plus ut. We could have more lags of y, more lags of x, and even more than 1x. So what the book says is let's go back to the example we've been looking at, which is an autoregressive model for GDP. Let me see which one they're using. So they estimated a model that I skipped. So an AR2 for GDP growth is estimated, and the data set is 62 to 2012. I'm going to just call it, I'm tired of writing GDPG, too much writing. I'm going to just call it y hat. So y hat t, this is GDP growth, is 1.63 plus 0.28 y t minus 1 plus 0.17 y t minus 2. So this is just GDP growth t minus 2 and so on. I'm just trying to save some writing. Then there's standard errors and so on. And you can use this model to forecast. I could find y t plus 1 given t hat to be 1.63 plus 0.28 times y t plus 0.17 y cap t minus 1. So you could forecast, just plug in the actual values here. This was 0.15 yt. Those aren't standard errors, those are the values. This one was 2.75%. And if you do that, if you plug it in, you'll get a forecast of 2.1%. So 1.63 plus 0.28 times that plus 0.17 times that is the forecast. So what the book wants to know is, can we add additional predictors to this model and improve our forecasts? So it says, okay, let's think about, and this has actually been in the news lately because there's this thing called the yield curve, and it's been flattening. So what the yield curve is the difference between long-term and short-term interest rates. Let's see, which ones do they use? Yeah, that's pretty standard. So they're going to use the 10-year bond rate minus the 3-month bond rate. So so it'll be the 10-year bond minus the 3-month bond rate. So that's called the term spread. And sometimes, and you can see it, there's a graph in the book I'm not going to duplicate because you can open your book as you're watching this and take a look at it yourself. But sometimes this yield curve will flatten and even turn negative. And when it turns negative, historically, often a recession has followed. It's not a perfect predictor because sometimes it turns negative and there's no recession, but often when it turns negative, there is. So the question is this going to help us forecast if we add this variable to our regression? We're just going to call it xt. Why would this work? Well, suppose you're very pessimistic about the future, so you think the future is going to be a whole lot worse than today. What that means is you're going to expect much lower interest rates in the future than you expect today, and then this is likely to get negative because this long-term rate will fall to reflect the future conditions which you expect to be worse, but this will end, it's only a 3-month rate, so it's going to be a higher interest rate because you're going to collect on that loan or whatever it is. You're going to collect on this bond before the recession is a problem. And so this is supposed to measure, in some sense, the market's forecast about the economy. And so you can just add that as another regressor to the model. And you'll get GDP hat. Now I'm back to GDP. GDP growth hat, is 0.95. Probably never should have switched to Y in the first place. Plus 0.27 GDP growth T minus 1. Plus, I need a little more room for the standard errors. Plus 0.19 GDP growth at T minus 2 plus 0.44. They call it the T-spread. T-spread. The term spread at T minus 1. And then they give you the standard errors. 0.49, 0.08, 0.08, 0.18. If you do the calculations, the T's are all bigger than 2, so this one's not quite, but the constant's usually not what we're worried about. And so everything's significant here. Then you could use this to forecast in the usual old way. We could use this to forecast GDP growth at t plus 1. In the data, it's 2013 Q1, based upon t, which is 2012 Q4. You would just plug in the values for GDP and the term spread, which are in your data set. And if you do that, you'll get 2.3. So the forecast error is actually worse than we looked at before. Forecast error, because 1.1 was the true value, is now minus 1.2%. And so it didn't actually improve our forecast. One thing I ought to point out, though, is looking at just one period probably isn't enough to evaluate whether this is a better or worse forecaster. It might be that most of the time this is much better, but there was something weird about this t plus 1 period that for some reason threw it off. So generally what you'd want to do is not just look at the forecast error in one period. You'd look over a bunch of periods, maybe 10 years or something, 5 years, and then take the average root mean square error as a measure of your forecasting ability, and you can compare two forecasts. That's this pseudo-forecasting stuff we'll talk about later. So although this looks worse, I'm not sure that this is a test we'd want to rely upon to make that conclusion. The other forecast was 2.0, which was closer to the value. But anyway, that's how you do this. So the general form of these models so the autoregressive distributed lag model, PQ, that's probably a lowercase q in the book. This is the number of AR lags, the number of lags of the dependent variable, and this is the number of lags of x. So you'd have yt equals beta naught plus beta 1 yt minus 1 plus beta p yt minus p. That's the p part, the AR lags, plus delta 1 xt minus 1 out to delta q xt minus q plus a ut. I really ought to be making that lowercase because that's standard to make them lowercase q's. This is really a lowercase p. That's just the way time series people write them, and so I should probably be consistent. And so that would be it. The model we just looked at was an ADL 2-1. We had two autoregressive lags and just one lag of the term structure. The book extends that to a 2-2. I didn't go through that. Didn't really help the forecast. But again, it wasn't really a fair test. All right. And we need the assumption that the expected value of ut, given all past y's and all past x's, is equal to 0. And that's just the usual thing. We need ut to be uncorrelated with the x's and uncorrelated with the right-hand side variables, is what I'm trying to say. All right. So that's the ADL. Let me do a little bit more, and then we'll stop this video, and I'll continue the rest of this chapter on a second one. So at this point, I wish the book would have waited a little bit, because we're going to actually talk about stationarity quite a bit more later on. But I want to stay in the same order they do, because so you can follow along in the same order the book does. So the book at this point talks about this thing we've talked about, stationarity. So here we're just going to define it, and later on we'll talk a little bit more about it. So with time series, we're using the past to forecast the future. So what we need is that we need the historical relationships to persist. Those historical relationships in the data can't change over time, or that will affect the accuracy of our forecasts in the future. So we need the future and the past to be sort of the same in some sense, that it can't be changing. And that's what this stationarity is going to give us. So the definition of that, so a time series is stationary if its probability distribution think mean and variance. If it's mean and variance, it also depends on higher moments. Remember, the mean and the variance are the first two moments of a series. That's all you need for normal. But for other types of things, you need all these moments. So what we're saying is all the moments of the probability distribution, which for the normal is just the mean and the variance, do not change over time. Does not change over time. Another way to say this, or, I guess that should be a capital O, the joint distribution of ys plus 1 out to ys plus t. Didn't write that quite right. The distribution of ys plus 1, xs plus 1, ys plus 2, xs plus 2, all the way out to ys plus t, xs plus t, does not depend upon s. So what is that saying? All right. Suppose y and x are correlated. Suppose that yt and xt are correlated and the correlation is 0.67. If I take the correlation at t equals 3 between y and x, it's the same as the correlation for t equals 87. That correlation doesn't change over time. If you look at the autocorrelations of a time series, say the correlation between yt and yt minus 2, it doesn't matter if I look at the correlation of y80 and y78, or y50 and y48, or y3 and y1. Those correlations have to be the same. If they're not, then it's not going to, then something's changed, and that past data won't be a reliable guide to the future. And maybe if you have something like, I'll talk about this a little more later, but like yt is beta naught plus beta 1. This is t, the actual time, plus ut, where this is normally distributed. The mean of yt for this, the expected value of yt, will be beta naught plus beta 1t. So when t equals 1, this is the mean. The mean is beta naught plus beta 1. When t equals 2, it's beta naught plus 2 beta 1. So the mean is changing over time. That would be non-stationary. This is that case where you've got, this is the beta naught plus beta 1t, then the ut causes you to just fluctuate around it. And so the mean value is not a constant. If I didn't have this, we'd be fine, because then it would be a constant, and the mean on average would be the same. So the expected value isn't changing. This is pushing us away, but the expected value of this is 0. And so the mean would be a constant. This would be stationary. So this is when beta 1 equals 0. You would have a stationary series. But we'll come back to this. There's a test for it called the Dickey-Fuller unit root test that we'll talk about. When we do it on the computer, you push a button or write one line of code, which is the way I hope you're doing it. Now let's generalize the ADL model. So, and then talk about the assumptions, and then I'll quit this video and go on to this second. So the generalized model, the general model is, it's going to take me a couple lines. Yt is beta naught plus beta 1 yt minus 1 up to beta p yt minus p. So that's that A part. And now we're going to add the distributed lags. But this time we're going to allow for more than one x plus delta 1, 1 x1 t minus 1 out to delta 1 q1 x1 t minus q. So there's q1 lags of x1, that's what that says, plus delta 2, 1 x2 t minus 1 plus, and I'm going to make this a different length so you can just emphasize that these q1s and q2s aren't necessarily the same. This should be t minus q1, t minus q2. And then we can keep going out to delta k1 xk t minus 1 plus delta k qk xk t minus qk plus ut. So p lags of y, k variables, and we're allowing them to have different numbers of lags. So you might have 2 lags of the term spread and 1 lag of something else, 2 lags of GDP, and 3 lags of some other variable. And so that would be the most general form of this ADL model. Most of the time, for reasons I'll talk about later, we assume that all of these Q's are the same, so the X's have the same number of lags. But you don't have to, and it's not always done. Okay, assumptions. They're mostly like they've always been. So the assumptions for the general ADL model. You write it as ADL of P, Q1, Q2 out to QK. So that's the shorthand note. When you write this, anyone who does time series knows you mean that big model we just wrote down. So this is a much easier way to tell people what you're talking about, with it save you a lot of writing. So what you need is first, we've been through this one, expected value of ut given y t minus 1 and its lags, x1 t minus 1 and its lags, out to xk t minus 1 and its lags have to be 0. Ut is independent of all the right-hand side variables, and that ensures it gives you the best forecast. 2a, the random variables y1t, or yt, t, x1t out to xkt have a stationary distribution. this is in some sense replacing the IID assumption that we've used up to this point. So up to this now, we've said that these variables are independently and identically distributed. Identically comes from the stationary part. We're allowing them to have some correlation, though, but what we want, if it's going to be stationary, we look at the autocorrelations, yt may not be independent of yt minus 1, but if we go far enough back, we get independence because those autocorrelations eventually die out to 0. So the correlation of yt and yt minus infinity is 0. So we have independence, but the independence is a little bit different. So we'll write that more explicitly. 2b is that yt x1t out to xkt and y t minus j x1 t minus j out to xk t minus j. So these two sets of things do just what I said. They become independent as j gets large. The autocorrelations die out. Basically, this ensures that the central limit theorem will hold. It gives us enough randomness. But that's not something I want to spend much time on. When this is violated, we have a non-stationary distribution. It really, really messes things up. That's why we'll spend so much time on stationarity. The third assumption is that large outliers, unlikely. That is, the data have non-zero, finite fourth moments. No different here. Same as it ever was. And again, same as it ever was. There is no perfect multicollinearity. Okay, so that takes care of almost half of chapter 14, and I will do the rest of the chapter in the next video.